Welcome to EENG 401, Electromagnetics. In this video, I just want to briefly introduce the topic of electromagnetics and give us a little bit of motivation as far as why it's useful to study electromagnetics. So, first of all, electromagnetics, which we'll often just abbreviate as EM, is the analysis, synthesis, physical interpretation, and application of electric and magnetic fields. So that of course covers a lot of different things there. Just to sort of give us a better sort of idea as opposed to this vague general definition, let's look at some common applications of electromagnetics. So we see electromagnetics are used in satellite communication, bioelectromagnetics, electromagnetic interference, which we've looked at a little bit at in a previous class, but of course you could get into a lot more detail as far as what's going on and how to prevent it, radar meteorology, plasmas, and nuclear research. So again, a vast sort of range of different areas. Some common EM devices, which hopefully you should at least be familiar with in one way or another, are microwaves. So of course we're using microwave radiation to heat our food. Antennas, so these could be large antennas transmitting things in space, or even small antennas like that are on your phone. Transformers, radio, TV, telephones, anything that's sending a signal over free space, transmission lines, and optical fibers. So again, the study of electromagnetics covers a vast amount of topics, and in a one semester course, unfortunately, we're not going to be able to touch on all of those, but hopefully you will come away from this semester understanding the basics and know enough to be able to apply sort of the basic principles of electromagnetics to solve topics in most of these areas. So our electromagnetics, or more specifically this material in the text, can be summarized with something called Maxwell's equations. And so hopefully that at least sounds familiar from physics or some other classes. So material and text can be summarized by Maxwell's equations. And so we're going to see there are 4 of them, and right now we're just going to introduce them. We're not going to be working with these until later in the semester. And these are on page 4 of the textbook. But again, the idea here is to just kind of show you where we're headed. So our 4 equations, I'm going to go ahead and write them out. And I'm going to come back and define some of these symbols and parameters a little later on. And of course, throughout the semester, we're going to be learning about each of these things to where we sort of have a better understanding of what these equations mean. Okay, and then I'm going to come back and make a note about some of the notation as well, not just the parameters, but some of these things I'm writing. And again, what we're going to do is we're going to spend the first part of the class sort of reviewing our basics so that we can get into doing some of these more complicated equations. So this upside down triangle that I'm writing, this upside down delta, is known as our del operator. And so what our del operator is going to do is it's going to let us perform differential operations on vector quantities. So this is our del operator, and it's our vector differential operator. So if we want to take a derivative of something that's in a vector form, which as we're going to see throughout the semester, pretty much anything with electromagnetics we're going to be doing very heavily with vectors. So that's going to be very useful to us. This other quantity here, D, in this first equation, this is our electric flux density. And again, this is something we'll get to a little later on in the course. But I'd like to go ahead and just define this so you guys are aware of what things are. We also have in this first equation this rho sub V, which is our volume charge density. So we can think of this as if we had, for instance, a cube. How much charge do we have in the cube? That would be our volume charge density. And again, let me just reiterate, you're not going to need to know these equations anytime soon, but just to give you an idea of where we're going. This B term is our magnetic flux density, so similar to our electric flux density, but now we're talking about magnetic fields. And we're going to see with these flux densities, it's essentially how much is going through a certain surface or a certain volume for a given sort of equation or field. Our E is our electric field intensity. and we'll talk about the relationship between our electric field intensity and our electric flux density later on. We see we have a partial derivative of that magnetic flux density on the right side of that equation. And then we have just two more terms down here. Our H is going to be our magnetic field intensity. And again, we'll talk about the relationship between our magnetic field intensity and our magnetic flux density. And then finally, our last term here is our J, which we should be familiar with from some other classes. This is just our current density. And so that's defined the same general idea as what we've used before with current density. How much current do we have in a given volume? So again, what we're going to look at in the text is essentially summarized by these four equations, which makes it seem kind of simple, but as we're going to see, we kind of have to do a lot to build up to get to a point where we can understand these equations and what's going on, what they mean. And we'll get there, but for now, don't worry about the specifics of them. A couple things about the notation now. So we'll notice that some of these letters have arrows over them, for instance, this D, whereas some of them don't, for instance, this rho sub V. And so what that indicates is that we're going to be dealing with vector quantities and scalar quantities. So in the above equations, if a letter or a parameter has an arrow above it, that indicates it's a vector quantity. So with arrow above it, indicates a vector quantity. And if we have no arrow above our parameter, like we had with this rho sub V, we had no arrow, then that's going to indicate that we have a scalar quantity. And we're going to come back later and we're going to define these in the next video and work with some of this, but it's important to note that we're going to have both vector and scalar quantities. One other sort of notation point, if you are going through the textbook, you won't necessarily see this arrow above the letter, like we see here again, for instance, but instead what you'll see is a boldface. So oftentimes in text, what you'll see instead of the arrow above is you'll just see the letter put in boldface. And so that's pretty common, but of course it's difficult to write in boldface and distinguish that here in this video or on a whiteboard or blackboard. So oftentimes when we're handwriting, we'll use the arrow to indicate the vector quantity. So we see we're dealing with vectors. We have vector quantities, scalar quantities. We have this del operator, which is for vector differentiation. And we're going to be doing integration for vectors and all of this fun stuff. So with that in mind, and with sort of the main goal of understanding these four Maxwell's equations, what we're going to do at the start of this course is we're going to do a bit of, hopefully, review. We're going to look at vector algebra. From there, we're going to move to coordinate systems, and then we're going to move to vector calculus. And we're going to spend a fair amount of time on this, even though it's not the exciting EM applications and devices we see here. It is very crucial that we have a good understanding of the basics before we're able to move to some of these more interesting applications.